Alright guys, we got a lot to get to in this video. We are introducing complex numbers. Get pumped. Alright, so this is lesson number 4 in my unit, I believe 8 lesson sequence. That changes from year to year, but we're looking at the polar unit. You'll see why in a second, why this is in the polar unit. If you want to check this stuff out in the textbook before we get started or after we finish, go ahead and look at pages 157 to 164 and 508 to 511. There's 2 spots in the textbook that kind of address this topic. So just because I'm doing so much in this video. What are we going to get to in this video? We are going to look at a new type of number. And then we're going to look at the basic operations, addition, subtraction, multiplication, and division with those new types of numbers. And then we're going to look at the 2 different forms, the rectangular form and the polar form of a complex number. A lot of this probably doesn't make sense yet, unless, of course, you've talked about this with me before. But it will make sense by the end of the video. So without further ado, let's go ahead and jump right in. The first thing I want to do is I want to take you back to elementary school. Maybe middle school. It kind of depends on when you started doing algebra. But I want to answer the question, what number, when squared, gives you the number 9? And a long time ago, forget algebra for a second, if you actually take yourself back to elementary school when you were first learning numbers, there was only one solution to this, and that solution was 3, because when you were that young, the only numbers you knew about were the natural numbers. But fast forward, take yourself to late elementary school, early middle school, right? Actually, probably still elementary school, right? If you were then again asked the question, what number, when you multiply it by itself, gives you 9, you had been introduced to the integers. And you may have said, okay, there are 2 things that when squared give you 9. Positive 3 and negative 3. Right? Fast forward. Now you're in middle school probably. And you are introduced to a new type of number. What number when squared gives you, not 9, because 9's a perfect square, but what about 5? What number when squared gives you 5? Right? In elementary school, you'd be like, nothing. You know, 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. There's no numbers between 2 and 3. Those, all I know are numbers that I can count with. So there was no solution to this. But once you got to middle school, you were like, oh, there's this new type of number. There's this number in between 2 and 3 that when you square gives you 5. And the answer was positive the square root of 5, or negative the square root of 5. All right, so we have natural numbers, we have integers, we have what we call the real numbers, right? These are things that you've become comfortable with, right? In elementary school, you probably were not comfortable or not even aware of these irrational numbers, right? Fast forward to now, all right? What if I were to pose to you the question, what, when squared, gives you a negative number? All right, we need to make sense of this because there is a solution. All right, it's not a natural number. It's not an integer. It is not a real number. All right, what when squared gives you negative 9? All right, so I'm going to leave this page. We're going to come back to this question. But I want to introduce you to something called I. All right, before I do that, let's jump to the number line. All right, let's give this thing some arrows because it goes on forever. Let's go ahead and put 0 in the middle. All right, but we have 0, we got 1, we got 2, we got 3. I'll go up to 4 in both directions. We got negative 1, negative 2, negative 3, negative 4. And what I want to do is I want to remind you guys what exactly it means to multiply by something. So let's say I have the number 1 on the number line. Right? If I were to ask you the question, what does it mean to multiply this number 1 by, like, what is 1 times, I don't know, let's go 3. Right? What is 1 times 3? You may say that 1 times 3 just means, well, you have 1 of something, and then you take that group of things and you have 3 groups of that thing, so 3 groups of 1, or you can think of it as 1 group of 3, so you'd go out here and say that 1 times 3 is 3. All right? But the way I actually want you to think about it is, imagine you have a ray. And when you multiply that number by 3, what you're really doing is, think back to geometry, you are dilating that thing. You're dilating the distance it is from the origin of our number line by 3. So here is some sort of distance, and when you multiply by 3, you take that distance and you dilate it by a scale factor of 3. That's what the number 3 does. All right, my follow-up question to that is, what if you take the number 1 and you multiply it by -2? What does multiplying by -2 do? Right? So you have the number 1. And you can think about this in many different ways, as I said with 3. But if I have the number 1 and I multiply it by -2, I want to think about that in terms of a dilation as well. So if I take the number 1 and I dilate it by -2, I'm going to scale by 2, but think about what that negative does in terms of geometry. All right? That negative passes you through the origin to the other side. Right? What was that exactly? That, multiplying by -2, isn't simply a dilation, but it's a dilation and a rotation of 180 degrees. Right? Multiplying by 3 is a rotation of 0 degrees and a dilation of 3. Multiplying by -2, multiplying by -a is a dilation of the number and then a rotation of 180 degrees on the number line. So it's now time to reveal what the heck this number I does. Right? So I'm going to give myself a new number line. I'm going to give myself a new origin. Right? Give myself a 1, give myself a 2. I'm only going to go out to 3 this time. And then go out to -3. Yeah, you know what? I got the room. Let's go out to 4. All right, cool. So I have the number 1. What does it mean to multiply by this new number I? What this number I's function is, it dilates by a scale factor of 1, so I, a number that dilates by a scale factor of 1 and rotates, right? -1 rotated 180 degrees. I rotates 90 degrees, all right? Multiplying by I rotates a number, dilates by 1, rotates a number outside of the real number line 90 degrees, sorry. What is that going to be? Counter clockwise. All right, so multiplied by I dilates by 1 and rotates 90 degrees counterclockwise outside of the real number line. Where does that take us? That takes us to a complex number line, and that is going to be right there. All right, so multiplying by I takes a ray of unit 1 and rotates it 90 degrees counterclockwise. All right, and that is what the number I does. So on this complex number line, what is 1 times I? Well, 1 times anything is that thing. So 1 times I is I. We're going to put I right here on this complex number line. All right. With that said, I'm going to quickly add the abbreviation RE for real and the abbreviation IM for imaginary. All right. That word imaginary is kind of a misnomer. These numbers are very real. We just call these numbers the real numbers and these numbers the imaginary numbers. All right, but these have a function. They're not made up. They have a real application in mathematics. So we have the number 1 multiplying by I gives you I, and that is 90 degrees counterclockwise from 1. We are now in the complex plane. All right, let's look at a few more of these. Let me give myself the first quadrant of the complex plane. All right, so let's say I have like the number 2. All right, so I have the number 2. All right, I'm on the real number line. What happens when I multiply by, let's go with like 3i, right? 2 times 3i, that's going to be 6i, right? 2 times 3 is 6, and then the I just hangs out. All right, but what does that mean functionally? That is saying dilate 3 units and rotate 90 degrees counterclockwise. All right, so I have 1, 2. I'm going to have 1, 2, 3, 4, 5, 6. I'm going to be way up here. You could also do the dilation down here. 1, 2, 3, 4, 5, 6. So you're going to have some sort of distance here too. You're going to dilate that thing by 6 and then rotate 90 degrees counterclockwise. All right, CCW. All right, so the final measurement here is going to be this number up here. What do we call this number? Well, if this is I down here, this is going to be 2i, this is going to be 3i, this is going to be 4i, this is going to be 5i, and then this will be 6i. All right, so multiplying by a scalar multiple of I does the same thing. It rotates 90 degrees counterclockwise, but it also scales. So 3i, also a very usable number, has the property that when you multiply by 3i, you dilate and rotate. All right, I got one more for you. What happens when I multiply the number 1, or any number that is, by I twice? All right, so algebraically, this is going to be 1 times I, that's I squared. Right? But what does this do on the number line? So let's go ahead and look at that. Here's a number line. Right? Here is a complex plane. All right, while I'm here, let me just remind you that this is not the Cartesian coordinate system. This is a plane, a number plane. It's similar to a number line, except it has 2 dimensions. All right, so we have the unit 1. Let's go ahead and put it right there. Right? And multiplying by I has the function of rotating 90 degrees. So whenever I multiply by I, I'm going to rotate 90 degrees. Right, so 1 times I is going to be I, but it's also going to be up here. Right? And what happens when I multiply I by I? I'm going to rotate 90 degrees again. Right? So when I multiply by I, no matter where I am in this plane, multiplying by I has the function of a 90-degree rotation counterclockwise. All right, so multiplying by I again gets me over here. And what is that on the real number line? That's -1. All right, wait 1 second. When you multiply by I twice, when you get I squared, that is functionally equivalent to multiplying by -1, a 180-degree rotation counterclockwise. All right, so there you have it. This is one of the most important discoveries that we need to address in this video, and that is I squared is functionally equivalent to multiplying by -1. That's the big idea. I squared is equal to -1. Right? Multiplying by I rotates 90 degrees counterclockwise. Multiplying by -1 rotates 180 degrees clockwise. So, counterclockwise. So, multiplying by I twice does that function twice, and it's equivalent to -1. All right? This is the money right here. Let's go back to the original question. All right? What when squared gives you -9? Well, multiplying by 3 twice dilates 9. And multiplying by I twice gives you a rotation of 180 degrees. Right? So 3I quantity squared is going to give you -9. Right? -9 has the function dilate 9, rotate 180 degrees counterclockwise. Like 3I has the function dilate 3, rotate 90. And if you do that twice, you get a 180 degree rotation counterclockwise and a dilation of 9. So x equals 3I is a solution to this question. What when squared gives you -9? What when done twice rotates 180 degrees and dilates 9? 3I. All right. And as well, we could just as easily do this with -3I, because -3I is going to dilate 3 and rotate 180 degrees, and then another -3 is going to rotate another 180 degrees. So total of 360. That's just the full rotation. So -3 and +3I when squared gives you -9. So we now have a new type of number. We have the natural numbers. We have the integers. We have the real numbers. A long time ago, this is all you had. This is all you had. All right, but then we introduced negative numbers. All right, that was completely new to you. Then we introduced real numbers, the numbers in between the integers. All right, not to mention the rational numbers. Right, fractions were a beast when you guys were doing them in elementary school. Very difficult. Now we have a new type of number, the complex number. All right, that's a capital C, boldface. Right? This is a whole new type of number that you are going to be comfortable with and is completely valid in terms of mathematics. So I have prepped the following diagram for you. Right? So the first type of numbers, and I'm going to be loose about the following set of statements, but the first set of numbers that you guys learned was the natural numbers. You were counting, you were learning how, you get 10 digits on your hands. You're using those to count apples, whatever. Right? So the first set of numbers that you learned were the natural numbers, and we use a bold N to describe those. Right? Numbers include 1, 2. My favorite number, 47. Right? These were numbers that you dealt with. All right? The next set of numbers that you learned, all right, later on in your schooling, you learned the integers. You learned about negative numbers. So you have -1. Oh, but you still have 1, right? You have 47, but now you have -47. So you introduced the negative numbers. And maybe 0. Maybe 0's here, maybe 0's here. It's kind of up to you, right? That's a whole philosophical question that you can answer on your own time. All right. But then we introduced the rational numbers. Right? Worst Q I've ever drawn in my life. All right, we introduced the rational numbers. So what is that? That's some sort of combination of two integers. Right? 1 over 2. Right? 47 over 3. Right? -6 over 5. Right? But also 1 was here. Right? 0's here. Right? -1 is here. Right? The negative numbers are still contained in the rational numbers. Maybe you see what I'm getting at here. Right? The next set of numbers that you learned were the real numbers. Right? And what fell in the real numbers? Well, you had irrational things like pi, things that cannot be expressed as the quotient between two integers. Pi, e. Right? You have the square root of 5. Notice negative numbers still are here. Right? -e is a real number. Right? But 1 is also still a real number, and -1 is still a real number. Right? Now we have what we call the complex numbers. And we have I, right? We have 3I, right? This has the function of rotating 90 degrees counterclockwise. This down here has the function of rotating 90 degrees counterclockwise in the complex plane, but also dilating 3, right? Negative 2I, right? This has the function of rotating, what is that? That's going to be 90 degrees clockwise with also a dilation of 2, right? But also, 1 is still contained in here. Negative 1 is still contained in here. These are complex numbers. All right, 1 and negative 1 are complex numbers. All right, I, 3I, negative 2I, we call those purely imaginary complex numbers. But they're still complex numbers. And for another day, maybe there's some more stuff out there. Right? We are going to be focusing on complex numbers, but maybe there are other types of numbers. Right? And this idea of number expansion doesn't end with complex. But that's another conversation for another day. With that said, let's proceed and start exploring I a little bit more. All right, so I. All right, I is I. Right? There's some people out there that say I is the square root of negative 1. No, I is its own number. Right? Treat it like it's such. You know, I always make this joke. My first name is Eddie. Right? If I pull that I out, right? People don't call me Eid, the square root of negative 1, right? People call me Eddie. Right? So we don't want to rename that letter I something else. We just want to leave it as I. But we can go ahead and say I squared is equal to negative 1 because they have functionally the same thing. Okay, so I squared is equivalent to negative 1. All right, we want to treat I the way it is. All right, we want to treat it like a new number. We don't want to lean on the real numbers in trying to understand this stuff. We want to accept it. All right, I squared is negative 1. All right, I cubed, well, let's go ahead and split this up. Let's do a little bit of expansion. I squared negative 1, this is going to be negative I. So I cubed has the same function as negative I. Well, is that true? Right? Multiplying by I 3 times is going to be, so I'm going to go ahead and put a point there. Multiply by I a second time, so this is times I again, times I a third time. You're going to get down here, all right, that's I cubed. And negative I, well, that's just in the opposite direction, 90 degrees clockwise. So multiplying by negative I is equivalent to multiplying by I 3 times. Right? So I cubed is equal to negative I. All right, what's I to the 4th? Well, that's just, that's going to be I squared times I squared, which is negative 1 times negative 1, which is functionally equivalent to multiplying by 1, so no dilation at all. We can keep doing this, right? We can do I to the 5th. Well, that's just I to the 4th times I, and I to the 4th was 1, so this is just I. I to the 5th is equivalent to I. I to the 6th, that's going to be the same thing as I to the 4th times I squared, which is negative 1. I to the 7 is going to be the same thing as I cubed, because it's going to be I to the 4th, which is just 1 times I cubed. So I cubed, that was negative I, and then I to the 8th. We can keep doing this forever. That's going to be 2 sets of I to the 4, which is just 1. So this is just 1. So we can keep this pattern going. So my question to you is, using this pattern, what is I to the 98? All right, this is going to kind of motivate the next thing that we do. So real quick, figure out what I to the 98 is. All right, so I don't expect you to find out what 9 is, and then 10 is, and then 11, and then 12, and 13, and so on and so forth, all the way up to 98. I want you to find this pattern. And if you notice, we can pull out as many I to the 4s as we want, and it won't change our final answer, all right? Because I to the 4 is 1, and multiplying by 1 doesn't change anything. So how many 4s go into 98? Well, it's just less than 100. 25 go into 100, so 20, we got, let me go back a little bit, I to the 4, 24 times. and then we have a leftover I squared. So what this amounts to is just pulling out how many quadruplets we have. Right, so we have I squared, which is -1. Right, and we can do this as much as we want. If you want to know what I to the 117 is, that's not a 17, that's a 4. All right, there we go. What is that? Well, I know that 4 goes into 116, so this is just I. All right, what is I to the 412? All right, I know that 4 goes into this number, so this is just going to be 1. Right, we have this little trick that we can do, but it does get better. So here is the this is called the rectangular form of a complex number, but this is just the arbitrary form of a complex number, right? So the number I would be when B is 1 and A is 0. All right, the number 3I would be when B is 3 and A is 0. All right, the number 1, which is a complex number, would be when A is equal to 1 and B is equal to 0. Right? And an arbitrary complex number is when A and B are non-zero. So let's look at some arbitrary complex number. Right? -3 plus 5I. All right? On the complex plane, where is this number? Well, it has -3 real parts and 5 imaginary parts, so that number is right here. Right? This is the number -3 plus 5I in the complex plane. Right? And we will soon discover what this number's functional ability is in terms of dilations and rotations. You can start guessing now. Right? But what I want to do before I start looking at what this is geometrically, let's do some calculations. So let's take -3 plus 5I, and let's look at addition. What happens if I add another complex number to it? So 2 minus 4I. Right? What is this going to be? Right? So the way we add complex numbers is we simply add their real and imaginary components. So -3 plus 2 is going to be -1, and 5 plus -5I plus -4I, that's going to be 1. So we have 1I, right? So -3 plus 5I plus 2 minus 4I, that's going to be -1 plus I. So what does this look like in the complex plane? Well, if I take, let me get a complex plane going. So real quick, if I take the numbers like 1 and, I don't know, 3, right? What is 1 plus 3? Well, 1 plus 3 is you take this segment, and then you take this segment, right? And you line them up kind of like head to tail. And then you end up with, what's 1 plus 3? Well, 1 plus 3 is, well, you take this segment right here, right? And you line it up, and you get 4. Right? 1 plus 3 is 4. So what does it mean to take -3 plus 5I and add 2 minus 4I? Well, where is the number -3 plus 5I? -3 plus 5I is 1, 2, 3, 5. It's going to be about up here, right? This is -3 plus 5I. Right? 2 plus 4I is 2, and then 4 is going to be down here, so there's your 2 plus 4I. Sorry, 2 minus 4I. All right? And then you have these segments. All right, my picture's not perfect. It's a little bit badly scaled. But I'm going to take this number 2 plus 4I and then add it to this thing. So I'm going to take its segment and then add it to this thing. And ultimately, it's going to become a -1 plus I. Right, we have I there. We have -1 there. So what does it mean to add two things? You're kind of lining them up as you do with normal numbers, right, on the number line. Right? It's really important that we understand what I is and what all these complex numbers are in terms of the complex plane. All right, let's look at some more. All right, so negative 3 plus 5i minus the quantity 2 minus 4i. What's that going to be? Well, we're going to do the same thing here, but with subtraction. We're going to do negative 3 minus 2, which is negative 5. And we are going to do 5i minus negative 4i, which is positive 9i. All right, so you can take a second to think about what that means geometrically. I'm going to proceed. All right, how about multiplication? What does that mean? All right, we're actually going to take a break from looking at the meaning, and we are going to just compute, all right, because there's a better way to think about the meaning of multiplication, but we want to get to that a little bit later. Right? So how do we multiply complex numbers in their rectangular form? All right, negative 3 times 2 is negative 6. All right, we're just going to distribute. All right, 5i times negative 4i, that's going to be negative 20i squared, and we know that I squared is just negative 1. So while I'm at it, let me go ahead and put a positive 20 there, but we have more. All right, we also have 10i and what is that, 12i. So we have 10i plus 12i, we have, what is that going to be, 20, sorry, not equals, plus 22i. And then, if we simplify this further, we get 14 plus 22i. All right, so that's subtraction and multiplication. And I'll let you guys, real quick, think about how might we divide these. I keep calling them rectangular forms because this describes kind of a coordinate in the rectangular plane. And let's do negative 3 plus 5i divided by 2 minus 4i. So take a second to try to figure out, how do we simplify this? How do we compute this? All right, so if you think back to when we wanted to simplify quotients that had radicals, we multiplied by something called the conjugate. Here we call it the complex conjugate. So let's multiply the denominator and the numerator, thus multiplying by 1, thus not changing anything, by the conjugate of the denominator. So what does this give us? Negative 3 plus 5i, 2 plus 4i. Let's do the numerator. We get negative 6. We're going to get a negative 20. That's going to be a negative 26. We're going to get a 5i and 2. That's a 10i. And we're going to get a negative 12i. That's going to be, what is that going to be? Minus 2i. All right, so that's our numerator. And then our denominator is going to be 4. All right, 2 times 2 is 4. All right, negative 4i times positive 4i, that's going to be a negative 16i squared, aka positive 16. You know what? Let me not jump so fast. That's going to be a negative 16i squared. I squared is just negative 1. All right, and then the rest kind of disappears because we're multiplying by the difference of squares. Right, 4i, negative 4i and 2, positive 4i and 2, that's going to go away. All right, so what is the final answer here? We have a negative 26. We have a 2i. In the numerator, we have a 4 minus, or 4 plus now 16, so a 20. And we're going to get negative 26 minus 2i divided by 20. And that simplifies to, what is that? Negative 13 tenths minus 1/10 I. All right, so keep in mind we can also have fractions when it comes to complex numbers, right? All right, rational numbers are contained in the complex numbers. All right, as I said before, we got a lot to get to, so let's go ahead and look at solving quadratic equations using complex numbers. All right, so how do we solve this? Well, you can factor. That's not going to work. You can do a lot of different things. We are going to just straight up use the quadratic formula. So negative b plus or minus the square root of b squared, 49, minus 4 times 1 times 15. You might be seeing the problem that's popping up here. All right, all over 2 times 1. All right, cool. And if you caught it before, like I said, we're going to have a negative number underneath radical. All right, 49 minus 60 is a negative 11, all divided by 2. All right, so back in the day, you'd stop and you'd say, there's no solutions. All right, there were no real solutions. All right, but watch this little trick. All right, negative 11, that's equal to negative 1 times 11. And negative 1 is equal to I squared. And we could take the square root of a square. All right, the square root of I squared, that's just I. All right, so 7 plus, now I times the square root of 11 all over 2. And we are now a complex number in standard form. All right, 7 halves plus or minus root 11 I. All right, a plus or minus bi. All right, so we have solved this equation using the fact that we now have I squared is equivalent to negative 1. All right, and you can plug this thing back in and it will verify this. All right, that's one of the motivations for this whole thing. We want solutions to this equation here. All right, and if I take this number here and I simply have the rule that I squared is equal to negative 1, that solves this equation here. Right? If I plug this in, I'm going to get something minus something plus 15, and everything's going to cancel out real nicely. I'm not going to do that in this video, but I leave that for you to do. All right, let's look at what these complex numbers do in terms of geometry. So let's say I have the complex number z. That's often the letter that we use. Let me get that out there right now. Is 6 minus 2i. So what the heck does this thing do? All right, so let's give ourselves a complex plane. All right, and let's take the number 1. All right, this is a really good way to figure out what this number actually does. So if we have the number 1, right, and we want to figure out what 6 minus 2i does, let's look at 6 minus 2i. So 1, 2, 3, 4, 5, 6, negative I, negative 2i. All right, this was a 6 way over here. Right, the number 6 minus 2i is way out here in the complex plane. Right, and what the number 6 minus 2i does is it takes the number 1, it dilates it out some amount, and then rotates it some amount. Right? How far did it dilate out? Well, we have the Pythagorean theorem. Let's figure that thing out. Right? If this is 2 and this is 6, negative 2, we could say. All right? If this is 2 and this is 6, then this magnitude is 36 plus 4 square rooted. So the number 6 minus 2i, using the Pythagorean theorem, has the property that it dilates square root 40. All right? And then it rotates. Well, what the heck is this angle? All right? This angle is, all right, the arc tan, or the arc sine, or the arc cosine, or whatever 2 of these 3 measurements that you want. I'm going to do tan, so that's going to be opposite over adjacent, so negative 2 over 6, aka negative 1/3. And the arc tan of negative 1/3 is, I've switched to the forbidden degree mode, it is negative 18.435 degrees. All right, so this number here, z, has the property that it dilates root 40 and rotates negative 18.435 degrees. And this is me graphing it in the complex plane. This is our rectangular form. With that said, let's look at what I believe to be the far superior form. Let's look at the polar form of a complex number. I'm just going to stop there with the complex number symbol. And we've kind of already done it. Let's look at, let me capture this. All right, let's describe this thing using polar. So it has a x coordinate, that is 6, and it has a y coordinate that's going to be negative 2i. Right? How can we describe this thing? Well, there's another way we can write 6, right? We can write 6 as the square root of 40 times the cosine of negative 18.435 degrees. Let me actually write a 3. Right? And we can write negative 2 as, right, the square root of 40 times the sine of negative 18.435 degrees. Sorry, I'm running out of room here. Right? And I can pull out, oh, there's an I. All right, let's not forget that I, that's there. All right, check your calculator. This is negative 2. This is 6. All right, we've constructed it such that that is the case. Right? Cosine of negative 18.435, that is the length here on the unit circle, then we scaled 6. Right? And then if I pull out this 40, or the square root of 40, I'm left with cosine of negative 18.435 degrees plus sine, or better yet, let me put the I up here, I sine negative 18.435. I keep writing 5s. What's wrong with me? Right? And that is kind of where we're trying to get to. Right? What is root 40? Right? Polar form. That is its distance from the pole. So we're going to call that r. Right? And then we have here cosine theta. That's its angle with the polar x-axis. Here it's negative. Right? Plus I sine that same angle. And this is what we call the polar form. And with this last little bit of room, I'm going to go ahead and write it like this. R CIS theta. And that's kind of just shorthand, R cis theta. That's shorthand for R cosine theta, I sine theta. All right? And this is how we'll be writing polar numbers as we proceed. All right? Because this angle is the same. This angle and this angle, they are the same. So I only need to write it once. R cis theta. This is the polar form. This is describing this point in the complex plane, just like 6 plus negative 2i is. All right. There are some things you need to worry about. Not worry necessarily, but this is unique. Right? If you're using the rectangular form of a complex number, the 6 plus negative 2i is the only way to write this number right here. But r cis theta is not the only way. Root 40 cis negative 18.435 degrees is not the only way to write this point. There are multiple ways to write complex numbers in polar form. Right? You could use a positive angle that has the same terminal end. If I want to graph the number 4 cosine 5 pi over 3, let me put parentheses there, plus I sine 5 pi over 3, aka 4 CIS 5 pi over 3. If I want to graph that, all I need to do is, let me make that more straight. There we go. That makes me happy. We need to graph 4 units away from the pole and an angle of 5 pi over 3 away from the polar axis. So 5 pi over 3 is going to be down here. And 4, I'm just going to go ahead and approximate right here. Right? So this is the number 4 cis 5 pi over 3. Another way to write this would be to say 4 cis negative pi, negative pi over 3. Right? This is equal to 4 cis negative pi over 3. Right? So there's multiple ways to write numbers in their polar form. So that's one. Maybe you might consider a downside. I don't necessarily consider it a downside, but polar does have its benefits, which let's get to. One of those benefits is this number, 4 cis 5 pi over 3, tells you the geometric function of this number. Right? The Cartesian, or sorry, the rectangular form doesn't tell you immediately the function, but this says dilate 4. Dilate by a scale factor of 4 and rotate 5 pi over 3 radians. Right? So this is one big advantage to the polar form, is that it immediately tells you the function in the complex plane of what this number does. You take some number, if you multiply it by 4, cis 5 pi over 3, it's going to dilate that number by 4, and then rotate 5 pi over 3. Let's multiply two complex numbers. So let's say we have the number, let's go with orange. Orange is not a number. Let's go with the number 6 cis pi over 6 times 2 cis 2 pi over 3. Right? So one way to do this would be to turn them into their Cartesian form, their rectangular form, and then distribute because you're going to have two components to both, and then condense, and then maybe convert back to polar. But what I want to do is I'm going to just use the laws of multiplication. So real quick, this is what it's saying is 6 cosine pi over 6 plus I sine pi over 6. All right, so we kind of are converting to its rectangular form here. 6 times cosine pi over 6 is going to be the real part, and 6 times I sine pi over 6. If we were to just simplify this, like actually calculate it out, we'd get rectangular numbers. All right, and then we have a 2 cosine 2 pi over 3 plus I sine 2 pi over 3. Cool. All right. Let's go ahead and just squeeze those 6's and 2's together. Let's make them a 12. And then let's distribute all this stuff out. So something beautiful is about to happen. Right? So cosine pi over 6 times cosine 2 pi over 3. That's going to just be cosine pi over 6, cosine 2 pi over 3. All right. And then we're going to have, let's go ahead and get the other two real parts. So I sine pi over 6 times I sine 2 pi over 3. That's going to be I squared. All right. I'm going to go ahead and write -1. And you know, I'm going to keep this going. We have I squared. And then we have sine pi over 6, sine 2 pi over 3. Right? And then we have the two complex parts. Or sorry, they're all complex. Sorry. We have the two fully imaginary parts. So we have plus I sine pi over 6 times cosine 2 pi over 3. Right? That's just this and this being multiplied. And then we have plus, and I'm running out of room. I sine 2 pi over 3. You know what? I'm going to write this as cosine pi over 6 sine 2 pi over 3. I just took this and multiplied them. I cosine pi over 6 sine 2 pi over 3. And you may actually see why I did that. Cosine, cosine, sine, sine, sine. Sine, cosine, cosine, sine. Cosine, cosine, sine, sine, sine. It's right in front of us. It's there for the picking. All right, so we have 12, but now we have cosine, cosine, sine, 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 right? What is this sign? It's actually a minus 1, all right, I squared. So we have cosine, cosine, sine, sine, sine. That's going to be cosine pi over 6 sine, sine, sine plus 2 pi over 3. All right, we just went from a bunch of cosines and sines to one cosine. Beautiful. And then over here, if we factor out that I, we have a sine, cosine, cosine, sine. That's going to be sine of the sum of the angles, pi over 6 plus 2 pi over 3. All right? You may now see why multiplying in polar form is amazing, because what we're going to get here is we're going to get 12 cis pi over 6 plus 2 pi over 3, right? 2 pi over 3 plus pi over 6, that's going to be 5 pi over 6. We're done. And look what we did, right? We started with 6 cis 2 pi over 3. Sorry, pi over 6. And we multiplied by 2 cis 2 pi over 3. And this ended up becoming 12 cis 5 pi over 6, or the sum of the two angles. All right, and this like makes sense geometrically. Think about it. 6 cosine I sine of pi over 6, that says rotate pi over 6 and dilate 6. 2 says dilate 2, and then the 2 pi over 3 says rotate 2 pi over 3. So what this is saying is if you multiply a number like 1 by these two numbers, you're going to rotate pi over 6 and rotate 2 pi over 3. In total, rotate 5 pi over 6. And you're going to dilate 6 and dilate 2. In total, dilate 12. Right? Multiplying, and this is like kind of the formula that you need to know. Right? Multiplying two numbers, R1 cis theta, and let's go theta 1, and R2 cis theta 2. Right? Multiplying two numbers in their polar form just says, hey, multiply the two magnitudes and add the two angles. Right? And that's what it means to multiply in polar form. You don't have to deal with this distribution anymore. If you are in the polar form, multiplication just becomes multiplication and a little bit of addition. Right? This is one of the huge benefits to being in polar form. You can really understand what the number is doing. It's a rotation and a dilation. Right? I leave it to you to prove this for all numbers. For all values of r and theta, for all complex numbers z. Right? I'll leave that as an exercise. I'll also leave as an exercise. So we got this one right here. Let me go ahead and capture it. I'm also going to leave as an exercise for you guys to prove that dividing two numbers. So if I have r cis theta, r1 cis theta 1, and I divide by r2 cis theta 2, all right, that ends up being the quotient of the two numbers times the cosine of theta 1 I sine theta 2. All right, the difference of the two. All right, so these are two facts of the polar form of a complex number. Let's do a quick division one. Like, let's show how powerful this is. All right, if I want to divide 4 cosine pi over 4 plus I sine pi over 4, and I want to divide by 2 cosine of 5 pi over 4 plus I sine 5 pi over 4. Right? There is no need to multiply by any conjugates. Or I could multiply by cosine 5 pi over 4 minus I sine 5 over 4 on the top and the bottom. All right, but there's no need to do that. I also don't need to convert to Cartesian. Rectangular. I need to stop saying Cartesian. But rectangular, I do not need to do that. All I need to do is take the quotient of the magnitudes. Right? This thing says to dilate by 4. If I'm dividing, this thing says to dilate by 1/2. All right, so all in all, we've dilated by 2 in total. Right? 4 divided by 2. All right, and then this says rotate pi over 4, but then rotate in the opposite direction 5 pi over 4. So rotate pi over 4, rotate in the opposite direction 5 pi over 4. That's going to be a total of negative pi. All right, and then what does it mean to rotate negative pi? Well, that's just multiply by -1. That takes us way back to the beginning of this video lesson. All right. Right? These two numbers divided by each other is -2. 4 times, what is cosine pi over 4? That's root 2 over 2. So let me actually backtrack. 2 root 2 plus sine of pi over 4. That's also root 2. So that's going to be plus I 2 root 2 divided by cosine 5 pi over 4. That's going to be negative root 2 over 2. So we have a negative 2 times root 2 over 2. That's a negative. And we're going to have the same thing over here. I negative root 2. All right, these two obnoxious complex numbers of the form a plus ib, when you divide them, you just get negative 2. Oh, you're done. All right, and being in polar form makes that really easy. With that said, I'm going to stop there. This video is kind of long, sorry. What I do want you to do on your own time, and I'll ask you guys to do this later, is prove these two formulas. All right, do what I did with the multiplication, but for arbitrary values of r and theta. And that's kind of the extension of this lesson is the proofs. All right, we looked at I, and we didn't just say, hey, it's the square root of negative 1. Please, please, please do not just go around saying I is the square root of negative 1, right? I is its own number. It has a function, rotate 90 degrees counterclockwise. All right, if I do that twice, I get the number negative 1. So conveniently, I squared is negative 1. All right, and then now we've looked at how to add, subtract, multiply, and divide numbers, both in their rectangular and their polar form. Next time, we'll look at some cool consequences of this, some cool corollaries to being able to multiply and divide in polar form. All right, but with that said, I'm going to close up here. I hope this video was engaging. Give me tips and suggestions if you want something new. I will see you guys later.